Okay, good morning. So we will be starting very soon. So we will start at 9 a.m. Okay, so let's start. So in the previous classes, we have introduced logic and then also predicate calculus and then also rules of inferences. And then today we are going to combine all of them together so that we can form the mathematical proofs. So first of all, we will introduce what is meant by a proof, and then we will talk about some methods of proving. And then in the next lecture, we will talk about some common mistakes in the proofs and then how to find a proof. So here, okay, so let's see. So a proof is a valid argument that establishes a truth of a theorem. So theorem is something that is we find it very important, and then these are something that we do not know whether it is true unless we have shown that it is true. Okay, so usually a proof is to show some important thing to be correct, and then this one is shown to be correct as the conclusion of a valid argument. And then inside the proof, we can have different kinds of statements which contain something called axioms. Axioms are something that we are believed to be true. There is undoubtedly it is true, and then there is no argument why it is correct. So we just assume something that is true. So for instance, when we talk about the traditional geometry, so we will assume that for any 2 points, there must be one and only one straight line that can passes through these 2 points. So these are something called the axiom. So we will not prove it, and then we just assume that it is true. And then these axioms, and then also inside the proof, there may be premises, just like any normal argument. And then we can also have other previously proven theorems, so that they are already established as something that is true always, so we can use them inside a proof. And then so these are something that we can find inside, and also we can have something new that can be created based on the rules of inferences. And then yeah, so finally the final step is usually the theorem itself, the conclusion. Okay, now I have some extra words to introduce to you. So first of all, what is meant by lemma? So we talk about theorem. Theorems are a very important thing that we want to show. But then lemma is some smaller theorem, minor theorem, that we are using it to help us to show the main theorem. So you can say that a lemma is a theorem that is not very important. So usually in a mathematical argument, we have a couple of theorems for a certain mathematical argument, but then to establish it, we have a bunch of helping lemmas to do so. So we expect people to memorize the theorem after reading the mathematical articles, but then the lemma, it is just something that is hidden inside. There is another word called corollary. So corollary is also a theorem. It is important theorem. But then corollary usually is a theorem that you can just prove it in one line based on some existing theorem. So for instance, let's see. So for instance, maybe so we may have some other examples later to see why it is correct. Okay, what is meant by corollary? And then the third one is called conjecture. Now, conjecture is something that is not true or not known to be true yet, but then people believe that they are true. So conjecture is something that usually it is made by important people, great mathematicians. So they suspect that something is likely to be true or something is likely to be false. So in that case, they made this claim and then hope that some other people can help us to see whether it is really true or false. But then conjecture are something that is not proven, but they are important thing that people believe. Okay, that we should study, and then probably they have high confidence. Maybe not that high confidence, but then they have a feeling that it is going to be true. More likely to be true than false. So some famous conjecture includes the Goldbach conjecture made by the mathematician Goldbach. So Goldbach conjecture says that for any even integer greater than or equal to 4, it can be expressed as a sum of two prime numbers. So for instance, 4 can be expressed as 2 plus 2 because 2 is a prime. Okay, 6 can be expressed as 3 plus 3, and then 8 can be expressed as 3 plus 5, 10 is 5 plus 5, and let's say we have another, let's say a larger number, let's say 100. Okay, so 100 you can express it as 3 plus 97, and so on and so forth. So far, nobody has been able to find a proof showing whether Goldbach's conjecture is correct, and nobody has a counterexample yet to disprove its correctness. So at this moment, even if we have used the computer to do the checking up to super large numbers, then there is still no counterexample. So nobody has yet found an even number that cannot be expressed as a sum of two primes. But then, is it true? Nobody knows. Yeah, maybe there is a super large number that we don't know, such that it cannot be expressed as a sum of two primes, but then nobody has found it, or maybe it is really true, but unfortunately at this moment nobody can prove it. So this is a kind of a conjecture. In computer science, there is also a famous conjecture. So computer scientists classifies some problems into two classes. One kind of problem is you can find a very efficient method to decide whether something is correct, okay, or whether the problem can be solved by a computer very quickly. There are also problems that although we do not know how to find the solution very efficiently, but then there are methods that can check whether somebody's answer is correct very quickly. So this is another class of problem. So the first class of problem, we call it the P class, and the second class of problem, we call it the NP class. So there is a famous conjecture or famous problem in computer scientists that they are studying is there a problem that belongs to NP, but it doesn't belong to P? So is there a problem such that it can only be checked, the correct solution can only be checked very quickly, but on the other hand, if you want to find the correct solution, finding is super hard. There is no efficient way of doing so. Is there such a case? So this is the so-called P, whether P is exactly the same as NP, whether these two classes of problem are the same. P equals to NP problem in computer science. So nobody knows whether P is equal to NP or P is not equal to NP. And most people now will we'll assume, not just assume, okay, we'll believe more it is the case that P is not equal to NP, so that we will use this as a conjecture or assumption in some of the mathematical articles, and then show the results based on this assumption. Okay, so this is conjecture. Okay, now so we are going to introduce some basic ways of proving things to be correct. The first one is called the direct proof. So a direct proof usually happens when we are trying to show a certain conditional statement P implies Q is always true. Now to show that P implies Q is always true, so one method here is we are assuming that P is true and then hope that we can obtain Q as the conclusion. Okay. Now if we can do something like this, then this is exactly the same as we are saying that P implies Q is always true, because to show P implies Q is always true, we are actually interested in only the case that P is true, and then if it is true, and then we always get Q as a conclusion, then P implies Q will be true. But on the other hand, if P is false originally, then we don't need to do anything. We know that P implies Q itself is always true. So in that case, so we can prove P implies Q to be true using this kind of method. So here is an example. So we want to show that if n is an odd integer, then n squared is odd. So what we are going to do here is, this is of the type of P implies Q. So n is an odd integer implies n squared is odd. So what we can do here is we start by assuming n is an odd integer and hope that in the end, finally, we get n squared is odd. So what is meant by an odd integer? Odd integer is an integer that can be written as 2 times some integer plus 1. So we will assume that n is equal to 2 times some integer k plus 1. Then using algebra, we find that n squared is equal to 2 times k plus 1 all squared. After expanding, we get it 4k squared plus 4k plus 1. And then if we rearrange the terms, so we will get the first part here is actually 2 times some number, 2k squared plus 2k. So this is also an integer, right? Yeah, k integer, 2k is an integer, k squared is an integer, 2k squared is an integer. Integer plus integer is integer. So this is of the form of 2 times a certain integer plus 1. So just now we have a conclusion that n squared is odd. So we, under the assumption that n is an odd integer, we get the conclusion n squared is odd. So in that case, we are just showing that the original argument, n squared is an odd integer implies n squared is odd, is always true. Okay, so this is an example. Now, this is another example, so let's go through it very quickly together. So here, suppose that m and n are both square numbers, then m times n is also a square number. So what we can do here is that this is of the form, this sentence implies this sentence. So what we can do here is, we assume the first one is true. So we assume that m and n are both square numbers. So in that case, m can be written as u squared for some integer u, and n can be written as v squared for some integer v. And using this assumption, we see what will happen. So using this assumption, m times n is equal to u squared v squared. And after we rearrange the terms, we will find that this is exactly the same as u times 3 this number all squared. So this is an integer. Integer times integer is an integer, right? So integer square. So m times n is of the form of some integer square, so it must be a square number. So done. Okay, so this is easy example, right? Now another way of proving is called proof by contraposition. So here again we are looking at some theorem that we want to show, which is of the form P implies Q. But instead of proving P implies Q directly, we are proving its contraposition instead. Now recall that P implies Q is logically equivalent to not Q implies not P. So this is called the contrapositive of the original implication, right? So to show P implies Q is true, it is equivalent to show not Q implies not P is true. So proof by contraposition is simply we show this one instead. Once it is shown to be true, the original P implies Q will be true. Now to show this is to be true, then it's easy. So we can now consider showing this by direct proof. So we assume not Q, and then we get not P. Okay, so this is the so-called proof by contraposition. So we will find that sometimes it is very useful. So for instance, this one. It says that 3n plus 2 is an odd integer would imply n is an odd integer. Now suppose that n itself is odd, we suppose that n that we talk about here is an integer. So we start with assuming that, okay, or fixing that somebody tell us that n is a certain integer. Now suppose that this guy further tells us that 3n plus 2 is also odd. Then we hope to get the conclusion that n is odd. Now we will find that if we try to use direct proof, then 3n plus 2 is an odd integer will not help us to go much far away, so that it's rather difficult to prove this directly. But instead, what we can try is we can try to use contraposition. So we will assume this is not true, and then hope that we can show that this is not true. So what we are assuming is we assume that n is even. So we begin with n is even, and we hope that in the end we can show 3n plus 2 is not odd. So which is saying that we want to start from n is even to show that 3n plus 2 is also even. Okay. Now when n is even, then n can be written as 2k for some integer k. Now we examine 3n plus 2 now. So 3n plus 2 is equal to 3 times 2k plus 2, and it is blah blah blah, and it is equal to 2 times some integer. So that 3n plus 2 is even. So what we have done? So we have done something like when the q part is not true, so not q, it implies that the p part is not true. So done. So we are just showing that the original P implies Q form statement is correct. Now another example. So this time, suppose that n, this time the value of n can be any real number, but yeah, any real number, or you can simply still assume that n is still an integer. That's still okay. Okay. Now suppose that n is equal to a times b, where a and b are both positive. Then we claim that, so this will imply one of these a or b will be less than or equal to square root of n. So this is what we want to say. So for instance, n is equal to 100, and it turns out that two numbers, after they multiply to each other, we get 100. So we know that one of them has to be less than or equal to 10. Now to show this, yeah, we can use the contraposition again. So we assume that this q part, a smaller than or equal to square root n or b smaller than or equal to square root n, is not correct. So if this is not correct, so this is of the form something or something. So we have De Morgan's law that tells us the negation will be, this one is not true and this one is not true. So what we can assume here is that we are assuming that both A and B, they are strictly larger than square root of n. So to make the negation of this part. So when A and B are strictly larger than square root of n, the product will be strictly greater than n. And if A times B is strictly greater than n, then we will know that n cannot be equal to AB, because not the same. One is strictly larger than this one, right? So in that case, if we start from the negation of the Q part here, and then after some logical deduction or inference, we get the negation of the P part here, then we are done. So we are showing that not Q implies not P, so that we are also showing that P implies Q to be correct. So this is the other example of proof by contraposition. Now the third one is called proof by contradiction, and it is a method that is super similar to proof by contraposition. So you will see, okay. So first of all, we see that this time we are not showing something. It's not necessary that we are showing a statement of the form P implies Q, something like this. So we can just show a simple statement, let's say a simple proposition P, to be true by this method, contradiction. So first of all, P is true. So the logical equivalence of P is the same as not P implies always false. To see this, P is logically equivalent to true. Always true implies P, right? Always true implies P. We claim that it is the same as P in logic. Because if P is true, then T implies P will be true, and if P is false, then T implies P will be false. Okay, so P is the same, is logically equivalent to T implies P, and T implies P is logically equivalent to its contrapositive. So T implies P is logically equivalent to not P implies F. So in that case, what we are showing here is that instead of showing P, we can show not P implies F. So the idea here is that we will assume that not P is true, and then we hope to get something like a always false. Always false is contradiction. So starting from not P, we hope that after certain logical deductions, we will get something that is always false in the end. So let's see an example. Now, so as I've just mentioned, this proof by contradiction is extremely similar to proof by contraposition. It is because we are actually using contraposition of T implies P here, right? P is the same as T implies P, and then T implies P is the same as its contraposition, not P implies F. So we are actually using proof by contraposition for the statement T implies P. Okay, so it is a special case of the proof by contraposition, but we will see. Okay, so it is something that is very commonly used. So we just give it an extra name called proof by contradiction. So here, let's see this example. So this example is itself of the form P implies Q, but then we can think of this as a whole statement. So let's see how we can show this statement to be true using the method of contradiction. So 3n implies 2 implies n is odd. So in order to show this is true, what we are doing here now is we assume that the whole thing is wrong. So we assume the whole thing is wrong. So this is of the form P implies Q. So this is wrong if and only if what? If and only if we can find a case that the first part is true and at the same time the second part is false. So what we are assuming here is we assume that the statement is false, so that we assume that the first part is true. We assume that 3n plus 2 is odd, and at the same time the second part is wrong, is even, n is even. Now we have 3n plus 2 is odd and n is even. But from the second part, n is even, we will do something similar as before. We find that n is equal to 2k for some integer k, so that we now get 3n plus 2 based on n is even, so that 3n plus 2 can be expressed as 2 times some integer. So what do we have? So we now have 3n plus 2 is even. So we now have this one. So this is something that we can obtain from the logical deduction here based on our premises. And then we also have a premise that says 3n plus 2 is odd. So this one and this one are the two statements that cannot be true at the same time. So we now have a certain statement, let's call it S, and then we also have another statement, not S, together to be true. So we arrive at a contradiction because we are saying that S and not S. Combining these two, we have the rule of conjunction. So this is true, but then we get false as a result. So we get a conclusion of false when we start with the negation of the whole statement here. So that is a successful example of proof by contradiction. Is that okay? So we start with something, the negation of the thing that we want to show, and then we arrive at some contradiction in the end. So that will just simply says that, oh, this one is correct, so that means that P is correct. Okay. Okay, let's see another example. So this is a super famous example. Okay, so this is some proof that is known, I think, more than 2,000 years ago. Okay, so it appears in the book written by Euclid. Okay, Euclid has a book called Elements. So this is one of the example that is shown there. So here we want to show square root 2 is irrational. So what is meant by rational and irrational? Okay, so a number is rational if it can be expressed as a ratio of two integers. And otherwise, it is not rational or it is irrational. So for instance, the number 7 is rational because 7, you can express it as 7 divided by 1. Okay, the number 0.5 is rational because 0.5, you can express it as 1 divided by 2. And then, for instance, 0.142857, so if you rotate it again and again and again, then this number is also a rational number. So it is exactly equal to 1 over 7. So we can have rational numbers, but then are there numbers that cannot be expressed as ratios between two integers? Yeah, the answer here is yes. Yeah, we can have a concrete example. So we are claiming that the square root of 2 can never be expressed as ratio between two integers. So how do we show this? Now, if you try to show this by direct proof, then what we need to do is we need to examine all the possible combinations of integers, and then you will need to find that none of them can be equal to square root of 2. But then this could be super tedious, or you may never be able to do that because there are infinitely many cases that we need to consider. So instead, let's try contradiction. So proof by contradiction here will assume that the whole thing, this whole statement, is wrong, and then hope to get some nonsense in the end. So when square root 2 is irrational, is what we want to show, we assume that it is wrong. So we assume that square root 2 is rational to begin with, and then hope that in the end we get something wrong. Now if it is rational, then what does that mean? So we can express it as a over b for some integer ab, and then we can also assume that b is not equal to 0 because when b is 0, we will not get an integer. Okay? And further, okay, if there are many choices of a and b, then we can always assume that a and b do not have any common factor. So for instance, so we have a number 2 over 8. So we can always take away the common factor from the numerator and denominator at the same time, so that we can simplify it to make it into 1 over 4. Okay, so when we have a over b, we can always take away the common factors from them, so that after doing this, then the a and the b will not have common factor anymore. Okay, so we assume that square root 2 is equal to a over b, and then a, b do not have any common factor. Now, because square root 2 is equal to a over b, then after squaring both sides, we have 2 is equal to a squared over b squared. So we will have a squared is equal to 2b squared. So that we know that a is even. Yeah, a squared is equal to 2b squared, right? So 2 times b squared, so it is an even number. Okay. Now, we have shown what? We have shown that if n is odd, then n squared is odd. So here, the opposite here is if n squared is not odd. So not opposite, the contrapositive is if n squared is not odd, then n is not odd. So this is the case. So if a squared here is even, then a must be even. That is, we can show this is true. Okay. Now because a is even, then we can now further write a as 2 times some integer c. So we get this form. And again, after simplification, we get b squared is equal to 2c squared. So that we get b is even. Now at this point, we find a contradiction. So the original statement is true. So what is the contradiction here? The contradiction here is we have already assumed a and b do not have common factor. But now we are showing a and b are both even. So a and b will now have a common factor of 2. So we get a contradiction. So these two cannot be true at the same time. So we are done. Okay. Okay, another case of proving things is called proof by cases. So here it is of the form of something like no matter P1 occurs or P2 occurs or P3 occurs or Pk occurs, no matter which case occurs, then we can always get Q as the conclusion. So let's say we are trying to show something like this, then what we can do here is we can simplify. We can simplify the proof the arguments by making a smaller part. So here, what we can do here is that, so here it says that no matter what happens, no matter P1 occurs or P2 occurs or Pk occurs, we will get Q. Then what we can do here is that we will show that if P1 occurs, we will get Q. And also if P2 occurs, we will get Q. And so on and so forth. And also Pk occurs, we can get Q. Then showing the first part is equivalent to showing this second part. And then showing the second part here is sometimes much easier than doing the whole thing together. Okay, now the logical equivalence between these two, you can use logical deductions, or you can draw a truth table for this. But yeah, I think you can you can use some logical argument to show why this is true. So let's see an example. Okay, so here this example says that if an integer n is not divisible by 3, then n squared is equal to 3 times k plus 1 for some integer k. Now here, an integer n is not divisible by 3, so there can be tons of them, millions of them, okay, infinite number of them. But what we are going to show here is that we are classifying the numbers into 3 groups. All the numbers all the integers in the whole universe into 3 groups. The first group is they are integers divisible by 3, and the second group is they are integers after division by 3 has remainder 1, and then the last group is they are integers after the division by 3 they have remainder 2. And then what we are interested here is that we want to show no matter what n is in the second group or in the last group, then the square of it is always of the form 3k plus 1 for some integer k. So n not divisible by 3 is equivalent to saying that n is either of the form 3m plus 1 or 3m plus 2 for some integer m. And then to show this original statement, we are going to use proof by cases. We show that if this case happens, then n squared is equal to 3k plus 1 for some integer k. We also show that if the next case here happens, then we will also have n squared is equal to 3k plus 1 for some integer k. Okay? Okay, so let's see. So if it is the first case, then n squared is equal to 3m plus 1 all squared. So here, the m here is integer, yeah, record it. So after expanding, it is 9m squared plus 6m plus 1, and then rearranging the terms, we will find that we can write it as 3 times some integer plus 1. So we are done with the first case. Now, if we have the second case, then n is equal to 3m plus 2. So in that case, n squared is equal to 3m plus 2 all squared. And again, after expansion and rearrangement of terms, then we will find that it is equal to 3 times an integer. This is a large integer, yeah, plus 1. So it is also true for the second case. So because no matter which case that happens, we will get the same conclusion. So we are done. So we are done with this case, we get the conclusion. This case, we get the conclusion. So we are just showing that no matter which case that happens, then we get the conclusion. Okay? Okay, we are having 2 more slides to go. Okay. And then the next one is proving by some statement of, we call it by conditional statement. So this is something that we want to show. We want to show that P if and only if Q is true. That means that we are showing that P and Q are equivalent statements. Yeah, P if and only if Q is true, is always true means that P and Q are logically equivalent, right? And then here, one way to show this is we are showing that P implies Q to be true, and also Q implies P to be true. If we can show these two together, then we have this one. So it is like if we start from P, we can get Q. If we start from Q, we can get P. So they are two the same. Okay. Now, in general, if you want to show, so first of all, this is something that is, I mean, not exactly a correct way to express what I want to say. Okay. This is, what I really want to say is that I want to show that all these P1, P2, Pk, they are logically equivalent. So I want to show that P1 and P2, they are equivalent, P2 and P3 are equivalent up to Pk minus 1, Pk is equivalent, so that we also have P1 and Pk, they are equivalent. Now to show that they are all equivalent, yeah. So what we can do here is that instead of showing all the pairs of combination, like P1 implies P2, and then P2 implies P1, P1 implies P3, P3 implies P1, P2 implies P3, P3 implies P2, and so on and so forth. We are not going to do something like this. We can do something very simple. We can just go in a circle. So we just need to show P1 implies P2, and then we also show P2 implies P3, and then we also show P3 implies P4, and so on and so forth, up to the last one, Pk implies P1. Now, just by showing the latter part, this is the second part here, to be true, it is enough to show that any two of them, they are equivalent. The reason is that we can use the hypothetical syllogism. So suppose that I want to show, somehow I want to show that P1 and P3, they are equivalent. But what we know is just this part. Suppose that we have shown that this part is correct. How do I see that P1 and P3 are equivalent? Yeah, because of the first two, we know that P1 implies P2 and then P2 implies P3, so we get P1 implies P3, right? But for all the remaining part, we have P3 implies P4, P4 implies P5, blah, 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 up to Pk implies P1. Then what do we know? Using hypothetical syllogism again and again and again and again, we will get P3 implies P1 based on the remaining part. So we get P1 implies P3 using the first two, and then we get P3 implies P1 using the remainder. So combining the two of them, we get P1 implies P3 and P1 implies P3 and then P3 implies P1. So equivalently, we are saying that P1 and P3, they are equivalent. So this is what we can do. So just by showing only these things, we can show any two of them, they are equivalent to each other. Okay, so this is the idea. Okay, we just show a simple example here. Okay, so this is a trivial example, but then you can see what we have the idea. Okay, so here we want to show that we have three statements P, Q, R, and then we want to show that any two of them are equivalent to each other. So the first one is P is saying that n is even, Q is saying that n minus 1 is odd, and then R is saying that n squared is even. Now, what we are claiming here is that they are equivalent. So I don't mean that P is true always, okay? I don't mean Q is true always. I just mean that whenever P is true, then Q must be true and R must be true. And whenever Q is false, then Q must be false, R must be false. So whenever one of them is true, then all the others are true. And whenever one of them is false, all the others are false. So this is what we are saying. We want to show that they are all logically equivalent. Now, in order to do so, so the idea here is let's try to use the method we see here at the bottom part. Let's try to show P implies Q, and then Q implies R, and also R implies P. So after we can show all these, then the three of them are equivalent. Okay? So P implies Q. If n is even, then n minus 1 is odd. So it is trivial because if n is even, then n is equal to 2k for some integer k, then Q will be equal to 2k minus 1, and then 2k minus 1 is equal to 2 times bracket of k minus 1 close bracket, and then plus 1. So it is of the form of 2 times some integer plus 1. So in that case, Q is also shown to be odd. So P implies Q is correct. Now the second part is when Q implies R. So when n minus 1 is odd, then we want to show that n squared is even. So when n minus 1 is odd, then n minus 1 is equal to 2 times k plus 1 for some integer k. Then n will be equal to 2 times k plus 2 for some integer k. And then n squared will be equal to 2k plus 2 whole square. And after expansion and rearranging the terms, then we will show that n squared will be even. So in that case, we can show that Q implies R is correct. Now the third one is R implies P. So R implies P is suppose that n squared is even, then n will be even. So to show R implies P, we can rely on, so this is already shown before, right? But we can rely on showing this by contraposition. Yeah, this R implies P is a standalone thing that we want to show now. We can use whatever method that we use. So we can rely on proof by contradiction, proof by contraposition, anything that you can imagine. So for this one, R implies P, we can prove this one by contraposition. So we assume that not P is true, then we hope to get not R. So we assume that n is odd, we hope to get n squared is odd. So this is done before. So that's it. So this is the so-called how we are showing the statements are equivalence by this circular thing. Okay, circular implication. So okay, so I think this is all for today. Yeah, so let's don't make it very hard for today. And then next time, yeah, we will talk about the remaining part of this set of slides, and then hopefully we will have some time to start the new topic, the mathematical induction. Okay, thank you very much. Yeah, that's all for today. Yeah, thanks. Let me see if you have any questions here. Okay, so far so good, right? Okay, so let's end now. So see you next week. Thank you. Thank you very much.